In the last lecture, we were solving transport problems in curvilinear coordinate systems, specifically in a cylindrical coordinate system. We were solving the problem of a startup flow in a cylinder. So, you have a cylinder with some fluid in it and which is initially at rest, and at time t is equal to 0, you rotate this cylinder with an angular velocity omega. Okay. And what we need to find out is how the velocity of the cylinder changes with time, how the velocity of the fluid in the cylinder changes with time. So, basically at initial time, okay, t is equal to 0, the velocity, the angular velocity within the fluid, in this case the linear velocity at a location r from the axis is the product of the angular velocity and the radius from the axis, okay, the distance from the axis. Okay. So, initially at t is equal to 0, v phi, which is the linear velocity in the phi direction, in the meridional direction around the axis, that v phi is equal to 0 for r less than r. Okay. It is equal to 0 everywhere within the cylinder, and at time t is equal to 0, you are imposing a velocity at the surface of the cylinder itself, angular velocity omega. Therefore, linear velocity there in the tangential direction is capital R times omega. Okay. And we want to know how the velocity evolves with time. The steady solution is when there is a solid body rotation. Okay. You recall that when we solved the steady state problem, okay, when we solved the steady state problem, we had got v phi is equal to a r plus b by r. Okay. That was the steady state solution for the flow between two concentric cylinders, okay, if you recall that. That was a steady state solution for the flow between two concentric cylinders. Okay. If you have flow within one cylinder, then this coefficient has to go to 0, otherwise the velocity will go to infinity at the center. Okay. And therefore, v phi has to be a linearly increasing function of r. That linearly increasing function has to satisfy the boundary condition, and therefore, the steady solution is just r times omega. Okay. Or if I define it in scaled coordinates, the steady solution is r star, where r star is the radius divided by the radius of the cylinder. We had expressed the solution as the sum of a steady part plus a transient part. Okay. For the steady part, the velocity is 0 at the center, and for the total solution also the velocity is 0 at the center. Okay. You recall that this condition emerged from symmetry. At the axis, r is equal to 0. V phi, if it is non-zero, it would imply that the angular velocity goes to infinity at the center. Okay. However, there is no physical boundary at the center. There is no physical boundary in the flow at the center. Therefore, the angular velocity cannot go to infinity at the center, and from the condition that the angular velocity is finite at the center, we find that v phi has to be equal to 0 at the center, just from symmetry. And as I told you, recall that this is different from what we had for temperature profile. In that case, the slope of the temperature was 0 at the center. In this case, the angular velocity itself has to be 0 at the center. So, the transient part has homogeneous boundary conditions. At the surface of the cylinder, the boundary condition for the total velocity is that v phi is equal to 1. The steady part satisfies the same boundary condition. Therefore, the transient part, which is the difference between the two, has to be equal to 0 at the surface of the cylinder. At r is equal to 0, v phi is equal to 0 and the steady part is 0. Therefore, the transient part is also equal to 0. At initial time, v phi is equal to 0, the steady part is independent of time, okay, and therefore, the transient part has to be equal to minus of the steady part. Okay. The steady part is proportional to r, it is independent of time. Therefore, the transient part has to be the negative of the steady part, okay, at initial time. and we got the equation for the steady part. It turned out to be identical. It turned out to be identical to that for the total solution, and we separated out the solution into a function of r times a function of time. Substituted in the equation, divided by f times g, and I got the left side only a function of time, the right side only a function of r, and that implies that both of these are equal to constants. Negative constants, because g has to decrease exponentially with time, so that the transient part decreases to 0 in the long time limit, and the steady solution is obtained. This was the solution, this was the equation that we got for f, okay. And I rewrote it slightly, okay. I substituted r plus is equal to beta times r, and then I get a solution, an equation, okay, and then I get an equation of this form, okay, which is the same as the Bessel equation for n is equal to 1. Okay. And that implies that the solution, okay, f has got to be equal to some constant a times j1 of r plus b times y1 of r plus, okay, where this subscript 1 implies that it is the solution of the Bessel equation with n is equal to 1. Okay. It is a solution of the Bessel equation for n is equal to 1. Okay. Just like the sine and cosine functions we had got in for conduction from a planar surface, and the solutions that we had got for J0 for the temperature profile, this is solution of this equation, okay, of this Bessel equation with n is equal to 1. Okay. And you can plot those solutions. Okay. So, if I plot, for example, as a function of x, I plot, okay, j1 of x and y1 of x. Okay. j1 of x passes through 0, okay, at the origin. Okay. It increases and then decreases, okay, and the amplitude decreases as x increases. Okay. Okay, I can write the argument as r plus. Okay, so I'll just use r plus for the argument. Okay, and since this is J1, I'll just I'll write it with the blue color. And y1 by the red color actually goes as 1 over r plus as r goes to 0. Okay. So, those are the numerical solutions. Okay. So, those are the numerical solutions that you get for J1 and y1. These can be found in standard tables, and you can also get numerical approximations for which you can write programs that will evaluate these. Okay. So, these are standard functions. Note that in contrast to J0 which we had earlier, this J1 actually is 0 at 0. Okay. It increases proportional to r, okay, at r is equal to 0. Okay. In fact, J0 is a constant, or it has 0 slope. J1 is proportional to r, you will find that J2 is proportional to r square and so on. Okay. So, those are properties of the Bessel function. Y1 goes to minus infinity. Okay. We know that at r star is equal to 0, which also is r plus is equal to 0. Okay. Note that we have defined r plus is equal to beta times r star, okay, where beta was the coefficient that we obtained, the constant that we obtained from separation of variables. Okay. Therefore, r plus is equal to 0. We know that the velocity has to be 0, which means that f has to be 0. Okay. And that is f is 0 at r plus is equal to 0 only if this constant b is equal to 0. Okay. Only if this constant b is equal to 0. Okay. And therefore, the solution for f that satisfies the condition at the axis is f is equal to a times j1 of beta r star, okay, r plus or beta r star. Okay. There is a second condition, second homogeneous condition at r star is equal to 1, okay, which implies that r plus is equal to beta, f is equal to 0. Okay. J1, this implies that j1 of beta is equal to 0. Okay. Okay. The condition that the transient part of the solution has a 0 boundary condition, has value 0 at r star is equal to 1, implies that j1 of beta has to be equal to 0. Okay. That means that beta has to be one of these, okay, it has to be one of these, okay, one of these 0 crossings of the function j1. Okay. And this crosses the axis at discrete values of beta. So, you will get a discrete set of values. Okay. So, beta, so let me write it here. Okay. This beta 1 is equal to 3.83, beta 2 equals 7.01, the third one beta 3 equals 10.17, etc. Okay. You get a discrete set of values at which it crosses through 0. Okay. So, this condition is satisfied only if beta has a discrete set of values. Okay. This condition is satisfied only if beta has a discrete set of values. Okay. Therefore, f has to be of the form a times j1 of beta n r star. Okay. G has to be of the form e power minus beta n square t star, okay, which means that the transient part of the velocity field has got to be equal to a times j1 of beta n r star e power minus beta n square t star. Okay. It has to be of that form. This form satisfies the boundary conditions that the velocity transient part of the velocity is 0 at r is equal to 0 and r star is equal to 1, and it satisfies the equation. So long as these coefficients in these two terms are the same, the equation is identically satisfied. Okay. And therefore, for any value of n, this combination satisfies the equation and the boundary condition. Therefore, the most general solution is the summation of these for different values of n. Okay, that is the most general solution, the summation of these for different values of n. And how do you find out the coefficients in this expansion? You have to use the orthogonality relation for the Bessel function, which I had proved for you in the previous in one of the previous lectures. Okay. In this particular case, the orthogonality relation is defined as integral r dr from 0 to 1 j1 of beta n r j1 of beta m r. Okay. Okay. You can show that this is 0 if n is not equal to m, and if n is equal to m, this is equal to j2 of beta n the whole square by 2 delta n m. Okay, that is the solution. Okay, that is, it is non-zero only when n is equal to m, and it is 0 if n is not equal to m. Okay. So, this condition has to be used to determine the coefficients from the initial condition that sigma n is equal to 1 to infinity a n j 1 of beta n r star, okay, at t star is equal to 0, that is the initial condition. At t star is equal to 0, these exponentials all become equal to 1, okay, and then you have to use this has to be equal to minus r star, negative of the steady solution. Okay. That is the initial condition, if you recall. Okay. Initial condition is that this is equal to minus r star at t star is equal to 0. Okay. So, the coefficients a n are determined using this orthogonality relation. Okay. That is the summation a n integral 0 to 1 is equal to minus integral 0 to 1 r dr multiplied by this term here r star, okay, times j 1 of beta m r. Okay. Now, the integrals on the left and right sides you can determine from standard tables or you can calculate it numerically. The left side you are guaranteed is 0 if n is not equal to m. Okay. So, therefore, on the left side I will get a m into j 2 of beta m whole square delta n m. Okay. This is a n. Okay, by 2. On the right side you can evaluate this integral and this will turns out to be equal to minus j 2 of beta n by beta n. I am sorry, beta m in this case, okay, because the right side contains only the index m. Okay, the right side contains only the index m, and therefore, this is equal to and this gives me the coefficients, right, because on the left side I am sorry I made a mistake, I have a summation n is equal to 1 to infinity. This delta n m is non-zero only when n is equal to m. Therefore, on the left side all terms in the series are 0 except the term for n is equal to m. Okay. Therefore, I can remove the summation, remove the delta function and set n is equal to m. Okay. So, this gives me the result for the coefficient a m, okay, is equal to minus 2 by beta m j 2 of beta m. Okay. Substituting that, I find out the value for the velocity v phi transient is equal to minus summation n is equal to 1 to infinity, okay, 2 by beta n j 2 of beta n, okay, times j 1 of beta n r star e power minus beta n square t. Okay. That is the transient part of the solution. The total solution is the steady plus the transient part. Okay. The total solution is the steady plus the transient part, which is equal to r minus sigma n is equal to 1 to infinity. So, that is the total solution. And once again this is an infinite series. So, strictly speaking it contains an infinite number of terms. However, you can truncate this at a finite number of terms if the time period t is sufficiently large, okay, because you can see that the beta n, okay, beta 1 is 3, beta 2 is 7, beta 3 is 10. Okay. What that implies is that the argument in the exponent is minus beta n square times t. Okay. So, for finite values of t, the term proportional to e power minus beta 2 square t will be much smaller than the term proportional to e power minus beta 1 square t, and so on. Okay. Each successive term will be smaller by a factor that goes as e power minus beta n square times t. Okay. Therefore, you can truncate it at a finite number of terms and get the solution only for this finite set of terms. Okay. And you can compare how many terms in the series are necessary to get a solution for a particular set of for a particular accuracy. Okay. So, let me plot, okay, V phi star versus R star. R star is equal to 1, okay, and here V phi star is equal to 1. Okay. This is the steady solution. Okay. The steady solution is a linear function. Okay. It turns out that the steady solution almost coincides with the transient solution for t star greater than or equal to 0.3. Okay. You get exactly the same solution as the steady solution. The transient solution turn out to be almost exactly the same, okay, for t star greater than 0.3. Okay. When t star comes to 0.1, there is a difference between these two. Okay. When t star is equal to 0.1, there is a difference between these two. Okay. And then for t star is equal to, so this is okay, and then for t star is equal to 0.03, it looks something like this, and then for t star is equal to 0.01. The velocity is close to 0 throughout the domain, but then it increases very close to the wall. Okay. So, you get something that goes like this. Okay. So, this is t star is equal to 0.01 is the lowest one. Okay. Now, I can look at the effect of 3 term approximation, okay, and the 1 term approximation. It turns out that for 0.03 and 0.1, the 3 term and the 1 term are almost on top of each other. Okay. For 0.03, the 3 term approximation still works quite well. Okay. The 3 term approximation still works quite well. Okay. The 1 term approximation shows oscillations. Okay. So, the 1 term approximation actually looks something like this. Okay. And at the earliest times, the 3 term approximation also shows some oscillations. Okay. It is not exactly 0 close to the center. Okay. And the 1 term approximation is very different. Okay. It actually goes negative and then it goes up. Okay. Okay. So long as the time is greater than about 0.1, even a single term is valid. 0.03 you can just use a 3 term approximation. For 0.01 you require a higher order approximation. Okay. It turns out that in this case as well, for very early times, okay, you can use the similarity transform. Okay. And I have a linear solution here. Okay. At very early times, if I take for example the solution for t star is equal to okay, this actually is in good agreement with the solution that I get by separation of variables, okay, of the form okay, where psi is equal to the distance from okay, so let me go back to my figure here. Okay. At very early times when the cylinder has just started rotating and the fluid is stationary, okay, when t is very small, the rotation of the cylinder, the momentum will diffuse to a thin region close to the wall. Okay. The momentum will diffuse over a thin region close to the wall, the thickness of which is square root of nu times t. Okay. So long as the thickness is much smaller than the radius, okay, root of nu t is much smaller than r, okay, or t star is much smaller than 1. Okay. If the diffusion time, if the time is much smaller than the diffusion time, then the penetration depth will be small compared to the radius of the cylinder. In this case, one can assume that this is like momentum transfer from an impulsively started plate into an infinite medium, so long as the thickness of this region is much smaller than the radius of curvature. Okay. So long as the thickness of this region is much smaller than the radius of curvature, then if this distance from the wall is r times r, I can define the scaled the similarity variable as this r minus r by square root of nu t. The distance from the impulsively started surface divided by square root of nu t will be the similarity solution. Okay. So, this is equal to okay. I can also write this as r into 1 minus r star by root of nu root of t, okay. And this nu t by r square is the scaled time. So, this is 1 minus r star by root of t star. Okay. So, if I use this transformation, okay, if I use this transformation and express the solution, then I get this solution which is almost identical to the transient solution, the exact transient solution for t star less than about 0.01. Okay. As t star increases, of course, it is when the penetration depth becomes comparable to the cylinder radius, this solution no longer applies, but at very early times this solution does apply. Okay. So, at very early times you can use a similarity solution, at later times you can use a solution due to separation of variables. So, this completes our analysis of separation of variables, okay, for a cylindrical coordinate system. Okay. So, this completes our discussion in a cylindrical coordinate system. I will start curvilinear coordinates, spherical coordinates in the next lecture. I will see you then.